Hello students, today's agenda is to check 1.1. We're going to have a small warm-up and then you are going to be able to apply appropriate units and you will be working on 1.2. Today students will be able to choose appropriate units and create a graph. Okay, so let's start with a little warm-up. It says choose the best unit, and so for the height of a building, what kind of units would you use? Well, we can say that we can use feet, okay? We can use meters, or we can use yards. Now, we cannot use, some of the ones that we cannot use for the height of a building are miles or maybe kilometers, because that would be way too much. The unit would be too big. For the area of a field, and be careful because some people get confused, area, it's not a linear unit, it's quadratic unit, okay? Square unit. And so for the area of a field, we can say that we are going to use square feet. So you can write it like that, or you can also write it like square feet. We can also use square yards, or you can write it like this as well. In some cases, I don't know if, I think this is good. We can use meters as well, square meters. Or like this, square meters. For the area of San Jose, California, well, again, we're talking about area, and that's a city. And so in here, we can actually say square miles or square kilometers, okay? So either one of these. I know that in some cases they use some of these. It's just that the number is going to be a little bit bigger. And what was I gonna say? This could also apply for area of a country if we're talking about bigger spaces, okay? And also distances of from one city to another will be similar, except that it wouldn't be squared because it's a distance, it's linear, it's going from one point to the other, okay? Okay, but not squared. Square is only for area. Volume of a jar. Well, first of all, we have to see that it's volume, and there is liquid volume and there is also space volume. So I'm gonna give you two different units. The other thing that we need to check is that it talks about a jar, okay? It's not talking about a pool or the ocean or bigger units, okay? So a small jar, which is like a container with food inside, like mayonnaise or jam, or I don't know what goes into jars, or pickles. Okay, so the volume of a jar could be ounces, okay, or maybe liters if they're a little bit bigger, like the big wholesale. And the other one is, if you're talking about the volume in space, it would be cubic inches or cubic centimeters. We wouldn't use feet, for instance, because that's huge. Okay, so for a small yard, it would be inches, centimeters, or ounces, and maybe for the little bigger ones, maybe liters, okay? Okay, so in here, I already have a drawing. Usually I ask students, draw a picture. I throw a ball of paper on the wall and I tell them to kind of draw if they were looking at that in slow motion in a video. And so when I ask them to draw me throwing the ball of paper, this is what they draw for the most part. So this is the wall, this is me, and then I'm throwing the ball of paper toward the wall, and then it bounces down, not as far as where I am standing, but a little like this. That's called the locus, which is the physical path of any moving object. Then together we graph the relationship of time compared to height in feet. And remember, I told them, imagine that this is a video in slow motion, because of course this happens is probably like 2 seconds and some segments of that. And so if they were to graph the height, I would put the height in here, which is the y value, and time on at the bottom, which is the x value. And it's time in seconds, considering that this is a slow motion video. This is the independent variable, so time just happens. But then the height of the ball of paper depends on how many seconds have gone by. Okay, so this is the dependent variable. Okay, so the height in feet is dependent on how many seconds have taken place. Okay, so I told them, if I have my ball of paper in here, okay, holding it, about how tall or high is the ball? And they say it's about 4 feet, which makes sense. And so at 0 seconds, it's in my hand, it's not moving, it's at 4 feet tall. After a second, I throw it, and after a second, like, how tall is it? Well, after 1 second, it's about 5 feet, they say. And after 2 seconds, well, it's about 6 feet. After 3 seconds, well, it looks like it's at 8 feet or so. Maybe here is more like 6.5. After it hits the wall, it starts bouncing down. I mean, it bounces and it goes down. Again, this is not the bouncing part, but rather, or how far from the wall, but how tall it is, the ball, okay? So after 4 seconds, well, it's around here, so they say maybe about 5 feet, because it's going down a lot faster than when it was going up. After 5 seconds, it's about maybe 2 feet or a little bit more, and then after 6 seconds, it's at 0, it's on the ground. So that's how they graph the tallness of the ball depending on the seconds, okay? And that's graphing relationships. Time compared to height, or height compared to time, okay? Again, this curve is not formed by the bouncing of the ball, but rather the time that is ticking and how tall the ball is, okay? Another relationship, and you know what? I'm gonna ask you in the assignment to actually come up with some data points. So for example, in here, we can have that at 0 seconds, so X represents the seconds. The ball is at, so the Y represents the height, at 4 feet tall. After 1 second, the ball is about maybe 5.2. I'm not gonna be exact, but after 2 seconds, maybe around 6.5 feet tall. After 3 seconds, it's at 8. After 4 seconds, and this is just a sketch, it's not perfect, it's about 5.5. Let me just put a 5. And then after 5 seconds, it's at 2. And then by the time you hit 6 seconds, it's already at the floor. So it's 0 feet tall, okay? So these are some data points, and X represents the seconds in all the points. Y represents the height of the ball in every single point depending on the second. Okay, so that's why the y is dependent on the x. Okay, so let's look at another graph, and this is the locus, the physical movement of my car when I'm taking my kids to their schools. So I start at home, and I literally make these turns, maybe not as exact as they look in here, but it's a sketch. And so I get out of the house, I turn, and then I turn once more, I turn, and I drop my son off. I come back into this street, and then I go and turn again, turn, and leave my daughters at their school. I come back, and then I stop in here, and I put some gas. Then I continue on that street, turn before that street, and then that's EP, that's Escuela Popular. So maybe if you're familiar with the streets around here, maybe you can figure out some of these streets. I can tell you that this is Gate Street, so you can imagine which one that is. Okay, so I go down here, and the relationship graph is actually the distance from home. I put homework in there. I'm used to homework. Home, okay? And it's in miles. So how far at any moment, how far am I depending on the minutes, okay? The minutes that I have driven. Okay, so I just put that I'm driving, and I'm just putting or plotting where I'm at after like 10 minutes, 20 minutes, 30 minutes. Like I just decided to choose this range of minutes, okay? If I did one by one, it would be crazy. And so that's where you have to decide the type of units that will be more appropriate for this type of graph. In here, I'm using miles, not inches, not centimeters, not feet, okay? So I'm using miles because I'm driving several miles away from home, and it would be too much to put it in feet. In 1 mile, there is 5,280, I believe, feet, okay? So we don't want to draw or have so much crowded in here. So choosing the appropriate unit. So I'm at home at 0 minutes. After I start driving, after 20 minutes, I'm 5 miles, and the reason is because this street is a little trafficy. Yeah, there is a lot of traffic in here, and there is a lot of traffic in here as well. This slow me down. Okay, so after 20 minutes, I get to my son's school. Then to my daughter's school, it takes me about 55 miles, okay? And again, it's because there is a lot of traffic in here and in here. More in here, but also a little bit in here. So my daughter's school is about 10 miles away, 9.5 miles away, okay? So from here to here directly, it's about that much, okay? I'm not talking about what I drove. That's the locus, that's the physical. I'm talking about how far from this point to this point. So from here to here, if I had to measure it, it's about 10 miles. Then I go for gas. From here to here is about 8 miles or so. And from home to EP is about 7 miles, okay? And it takes me from here to here about 7 to 10 minutes, so I just put 10 more. And from here to here, another 7 minutes to 10, okay? So that's why it's like this. So I'm gonna put, and again, it's not exact, I'm just gonna see, so I'm gonna put 0, 0 in here for the data points, and then 20 and 5 miles when I'm at my son's school. My daughter's school, I would say about 55 miles. 55 minutes later, about there, so about 9.5 miles. Then when I go to put gas, I would say about 60. Only 5 minutes to get there. 6 minutes or 7 even. And I'm at 8 miles away from home. And finally 65. After 65, meaning 1 hour and 5 minutes, I'm at EP, which is 7 minutes. Okay, 7 miles. And so those will be the data points that represent this. Again, this is how far I'm, depending on the moment that has taken place. Okay, how many minutes later, where I'm at. And this is just how far I'm from home. And you can see that EP is closer to my house. So if I had to go just directly or like this, it will be a lot faster. Okay. Okay, so with this, you're able to work on 1.2. You're going to be creating, not this, you don't need to do the locus, the physical path, you don't have to do it unless you want to. But you do have to create this. You are going to have to choose the unit, and you're going to give me some data points. So do 1.2 and have fun.